Good afternoon, friends. And my speaker at the same session, Mr. Geherwar. Sorry, his name was not pronounced properly. Geherwar. Uh, so, what I'm going to talk about regarding bridges is designing bridges for resilience. That's the key word. And this is, as you know, a part of the climate change scenario. These are the three parts of my presentation, and we will stop whenever we are told to stop. Okay, so as you can see in this slide, that you have the UN Disaster Risk Reduction Program Report 2025, and they have said that we must shift from reactive response to proactive investment, which means that there should be investment if you want the infrastructure to last long enough for the design life of it. Then you have to invest in it, not start repairing it when something goes wrong. As you may be knowing, the three pillars of sustainability, as recognized, are the environmental aspects, social, economic. So these are what the sustainability, when we talk about, that's what it means. When we talk about resilience, although they are connected, but it really stands for robustness, redundancy, and repairability of the structure. So, what is bridge resilience? As you could see in the first slide, sorry, I'm going to go back a little bit. As, if you remember, there are these two boxers which are there, and obviously there is one which is stronger than the other, or stronger than what he had anticipated, and there is a referee which is started his countdown. If this gentleman who has been knocked down, he can get up before the count reaches 10, then he is resilient. That means that you may be subjected to a superior adversary, but even after having got knocked down, if you can come up quickly, then it is resilience. So resilience definitions has this very good example in a boxing ring, but it depends, like I said, on robustness, redundancy, and repairability. And each one of them, when we talk about structural engineering, robustness means is that in case of an accidental action, when the load exceeds the design value, there should be minimum damage. Redundancy means that there have to be alternate paths of transfer of forces. Supposing one path is blocked or it is damaged, then the force should still be able to transfer. That is redundancy. And repairability, of course, means that in case there is a damage, you should be able to put it into functional mode as quickly as possible. So, the current state, the philosophy of design is called limit state design, and it consists of majoration of loads, which means that basically you are increasing the loads from whatever the design value is, and there is a minoration of strength. Minoration of strength means that you may not get the same strength, although it is made in steel and in a factory, but still there can be variations in the quality of that steel. So you reduce the strength, you increase the load effects, because the load effects are also, you may assume something, but it may be higher than that. So, in the future, what we have to do is that apart from the existing things that we are doing, we have to factor in climate change in order to be resilient and future ready. If you are mathematically minded, you can see that equation below. It's just that the loads must be less than the resistance, and there are some factors which are given before that. This eta factor that you see, that is what has been introduced to take account of resilience and future to be future ready. So, what are the main causes of bridge collapse? Somebody has made a worldwide study, and they have found that it's really natural disasters which uh, which account for the most collapses of bridges. But of course, there are um, other reasons for collapses also, which are mentioned here in the slide. If you look at all the vulnerability issues and you look at all the infrastructure types, at the top you can see the what are the various types of infrastructure: pavements, bridges, drains, rail tracks, culverts, side slopes, coastal, ports, airport, etc. So these are all the types of possible infrastructure, and the vulnerability parameters are rising temperature, rainfall, wind, cyclone, etc. If you look at under bridges, all these have been crossed. So all these effects are important for bridges, which may not be so for all the infrastructure, but for bridges it is. This is called the bridge resilience triangle. This is what you have designed for, and it may be exceeded, this particular forces, and the functionality is shown here. So the forces may be exceeded and it may be somewhere there. On the x-axis is the time. So if you look at this AC and AB, so AB represents the vulnerability, as is clear, and this triangle area has to be made as minimum as possible. Although it is called the resilience triangle, it is the loss of resiliency for various reasons that comes into the picture. So you can integrate this, or you can just multiply it. It's just a simple thing. And there is an angle alpha here. This is important because if the angle becomes larger, the resilience triangle becomes smaller, and that's what we are aiming for. Now, we mentioned about the natural disasters. One of the most important things is the scour and the amount of water that flows, or floods that flow in the river or any stream. All that is important. So there is a more recent application. Of course, it's already 2017, but they have made a study of 33 major rivers in India, and they say that different formulae, which are all empirical, decide what to use for large and small streams or rivers, which formula to use in order to be able to evaluate the discharge. This A, incidentally, is the catchment area, but there are, as we will see, there is not only the catchment area, there is also other things that come into the picture. Now, the main Himalayan rivers are the Indus, Ganga and Brahmaputra. They are all fed by, all three are fed by rain as well as snow. So that is why they are more or less perennial, and about 80 to 90% of the annual rainfall over most parts of India falls during the southwest monsoon. That is between June and September. There are places where the river changes course, which are very difficult to control. And good examples are Kosi and Gandak. The Kosi River has changed course by 140 kilometers over the last 200 years, as you can see here. So it requires protection, because normally all these barrages and embankments and all that have not worked, but something more sophisticated, which has been proposed by the Central Water and Power Research Station, needs to be done. This is what happens to the flow. I mean, when you come to a bridge, the flow gets constricted, and therefore the velocity increases locally, and you get the points which are marked at these 4 locations. They are most vulnerable to scour. So there are 3 main types of scours. One is a general scour, that means there is a lowering of the river bed when there is a flood. There is contraction scour at the bridge, and then there is a local scour if you have an obstruction. So here, if you see, this is the pier of a bridge, and you have the water flowing, and how the scour is taking place locally. And of course, if this does not have enough embedment, you will get a failure of the whole bridge. So what is happening during climate change is that your high flood level is likely to be higher because of excessive rainfall, etc. And if you have more high flood, you will get more discharge, and as a result, the scour will be much more. So the grip length that you had originally, what we are designing for, may not be adequate. So because if that scour becomes lower, then you have a lower grip length, and that can be quite dangerous for the bridge. So we have to take this into account when we are designing for resilience. Here you can see a well foundation or caisson foundation. 4.5 meters of it has been eroded, and now the bed level is somewhere here. Previously, it was somewhere here at this place. So this lowering due to local scour can undermine the foundations and therefore result in collapse of the bridge. Overturning and sliding is another. We have had many accidents and failures in bridges in India which are on a curve. And here you can see something on the border roads where you have a curve, and there were 2 or 3 truck drivers who parked their car on the outer periphery of this and went for a cup of tea or several cups of tea or something more stronger, I don't know what. But when they came back, they found that neither they could find the bridge nor their trucks. They were all, if you can see them, these are the trucks which were there originally. And of course, the bridge is not there, and they really did think that somebody had spiked their tea or something like that, because they couldn't see the bridge and they couldn't see their vehicle. So this is what can happen. It's a very simple thing, but even under its self weight, the bridge is not stable unless you design for it, and you have to have a larger factor of safety. You have big transports. This thing is on logistics, and people are trying to send more and more things on heavier and heavier vehicles over the bridge. So for which the bridge has to be designed, and overturning is something which is definitely an embarrassment for everybody, including the owner, the designer, and also perhaps the person who's responsible for the overturning. Here you can see the other, even during construction, a curved bridge has fallen the moment we tried to decenter it. Here you can see something in Calcutta which is the Ulta Danga bridge. Here you have a very sharp curvature, and what actually fell was this, which is got a less curvature. So it requires some thinking. People thought that if this one is safe, then why should something which has got a smaller radius of curvature? It is not only radius of curvature; it depends on the span and the angle subtended by the thing. So that is the reason why it fails, and this is a great. It's a pity, but that's what's been happening in India. This. Okay, so I will just show one or two examples, and whenever you want, we can finish. Here is something which is not got redundancy. You have an arch bridge, and it's got a single rib, which divides, of course, into two, and it has got a single set of suspenders. This is not redundancy, because you can see the progressive collapse, what happened, and all because of lack of redundancy. So you should not have a single rib and just one layer, one plane of hangers. On the other hand, if you see something like this, which we designed for the near Kullu, the Parvati River, it has got two ribs. It has got suspenders which are again suspending the deck on both sides. Now this type of a thing gives you redundancy. In case there is a failure of even a single suspender, it should not result into a major collapse. It should be still there. Okay, thank you very much for your kind attention.